So today we have Professor Robert Walsh, who's from UCLan, who's going to be talking to us about his work and the work of others with the sounding rockets from the NASA program. And it's something I'm very interested to hear about. So without any further ado, please, Robert, take it away when you're ready.
Thank you very much, Chris. Good morning, everyone. Hope you're doing okay today. It's brilliant to have this opportunity to finish the series. I was meant to speak earlier on in the year, but due to various reasons that had to be postponed. So it's good to join you here and send you off, launch you off into the summer over this seminar series of, in this case, about rocket science. As Chris says, it's work I've been doing at the University of Central Lancashire, and working with NASA for a lot of the time. And I'm here to try and tell you a bit about the stuff that we've been doing at the University of Central Lancashire. And given the time I have, it's probably better just to focus upon that. So let me just see if we can get this right to that slide. So, well, what are we going to do today? We're going to find out what is a sounding rocket and why we use them. I'll give you sort of basic introduction to the anatomy of what a rocket is and the various phases and launches and when the observations and everything take place. There have been many solar sounding rocket experiments. Given the time we have, I'm just going to focus upon some results from two of them as shown here. And then what next? What are the opportunities moving forward for sounding rocket work to take place? But in order to talk about sounding rockets, then you've got to see one actually being launched. So here we go. If that hasn't woken you up, I don't know what has. I apologize if you're sort of semi-deaf now, really, for a moment. This is a launch we're involved with the High Sea mission. And this is what I'm talking about. This is what we're trying to get. How we can use this particular facility, this particular way, this particular low-cost access to space in order to actually use it for scientific purposes. Sometimes a large multi-instrument mission put on a big giant rocket is the best way to go. This Swiss Army knife, I suppose, of multiple tools and objectives and uses employed in many different ways and working together to deliver a particular goal. But also sometimes you need something else, something more targeted. Maybe something like, this is an image from Crocodile Dundee. I don't know if you've ever seen Crocodile Dundee. It's probably before some, if not the vast majority of your time. It's streaming on Netflix. Other streaming services are available. But in this bit of the movie, somebody tries to mug Crocodile Dundee and pulls out a knife. And he says, well, you think that's a knife? This is a knife. Well, sounding rockets are, well, like this is a knife. This is a very targeted piece of equipment that actually is key to getting a very tight, focused answer to a science question. No messing about, a blooming big knife to make some sort of headway on a very, very specific problem. That's really what a sounding rocket is trying to do. So what's the definition of a sounding rocket then? A sounding rocket is an instrument that a carrying rocket that is designed for research purposes, such as taking measurements and performing scientific experiments, but during a suborbital flight. It doesn't actually reach orbit. It takes a parabolic trajectory up, has apogee, the top of its particular trajectory, and then re-enters the Earth's atmosphere downrange from the launch site. They take the name from actually the nautical term to sound, which of course means to make a measurement out at sea down into the depths to sound from a sonar perspective. And NASA has been sort of running this sounding rocket program for probably over 50 years now. It really is a critical scientific and technical and educational contribution that the Sounding Rocket program makes to the wider space program. It's very robust now, very versatile, as we'll see, and cost-effective way for you to test and to get into a low-gravity environment, into space. So a wee bit of history, just to warm you up here this morning. This is Werner von Braun. He really is, I suppose, known as the father of rocket science. He was a German aerospace engineer. Now, without his controversies, I suppose, he was a leading figure in the development of Nazi rocketry in World War II. And we know all about that, particularly here in the UK. Well, at the end of the Second World War, he was snaffled by the Americans, along with many other of his colleagues, to have a sort of second career in the the US space program, and to mastermind elements of that. You know, he became the director of National Marshall Space Flight Center, and of course was the lead architect for the Saturn V rocket program, which propelled the Apollo spacecraft and then the astronauts up to the moon. He's known for many different quotes that he actually gave us. One of his quotes here: the basic research is what I'm doing when I don't know what I'm doing. And therefore, if you bump into your supervisor or whatever, or your project lead, and you don't know what you're doing, just basically tell them you're doing basic research, because that's what it's really all about. I managed to find a little movie of von Braun. Here he is, beside one of these repurposed V2 rockets out at the White Sands Center. Here they are, you know, filling up the rocket with fuel, very similar to what we do today, as I want to show you with some photographs from more recent launches. They're doing checking everything and turning valves and doing what you do. Here they are, putting the nose cone on, and here it is taking off in a very sort of majestic manner, but the shape and style very similar to what maybe Elon Musk is trying to do with SpaceX at the moment. And here's all the crowd of the Rocketeers doing this stuff, probably nearly about 50 years ago. You can actually go to the museum at White Sands Missile Range and see one of the V2 rockets. It's one that I was so recently. It's brilliant to actually see that, a piece of history that shows where we've come from as we try to understand the uses of sounding rockets today. So why would we use them? What is the given what you can do with a rocket? What's the advantages, and why should we be involved in it? Well, you know, you can design a proposal for a sounding rocket in a couple of months, really. That can go right through the NASA program, particularly low cost access to space, but other technical programs that they have in place. And you really can go from, you know, a proposal acceptance to data analysis, probably in about, you know, between 1 and 3 years, and usually around about 2 years, really, as opposed to the many years, if not decades, that you have for a typical satellite mission. The only trade-off, and it is a major one in some respects, is that you only get to be about 10 minutes worth of time in space. I'm going to show you examples of that. Well, some of the observations we have are just a matter of minutes, but what a matter of minutes, what a 10 minutes you get, because you're able to do things that you wouldn't be able to do otherwise. You can use the sounding rockets, of course, to develop and test new scientific instrumentation before, therefore, it goes on to more costly, long duration orbital missions. You know, they really are an alternative because you don't need you know, expensive boosters here. You don't need extended telemetry or the tracking coverage. You literally, as I'm going to show you, a couple of rooms, you send this off and you track it in its particular pathway. Because they never go into orbit, that has its advantages as well. You also have a situation, there's a high degree of commonality, really, a lot of reuse when it comes to a sounding rocket. In many cases, it's just basically the experiment that changes, the experiment that provided by the instrument team, but everything else around that stays fixed, and therefore it is a very cost-effective way. You know, in most cases of astronomy and planetary and particularly solar science, the payloads are recovered, which means you can reuse elements of that, and therefore if you've several launches, the overall costs of your program reduce even further. So it's a very positive way of actually reusing what you've got and not wasting anything in the program. So you can develop some of these payloads very quickly, and this has been done in not very often, but in some cases, sometimes down to about 3 months, really. You know, particularly, for example, if you have a new phenomenon, one of which was one good example was the Shoemaker-Levy comet impact at Jupiter, where they quickly put a rocket up in order to be able to take some specific observations at that time. But also, and one real advantage is you can incorporate the latest up-to-date technology in your experiments. You don't have to, you know, design something and then, you know, 5 years later, it's not what you would want to do. You can take in some respects, latest technology off the shelf, or the latest ideas and concepts you have, and put it into something that's actually going to go into space. There's a lot of really good reasons for that, and in particular, you know, that has helped in the States in particular, that we've had some of our PhD students involved in this program at the University of Central Lancashire, a way for graduate students to gather data which goes into the PhD from, you know, from design and from idea right the way through to actually gathering the data and analyzing it. And I should also say for the geospace areas rather than solar, you know, the mission gets to an area where, you know, a low Earth orbital mission wouldn't actually reach. So you actually can sample then a bit of the Earth's upper atmosphere that you wouldn't be able to do otherwise. So lots of really good things as to why sounding rockets are useful to us. There's a number of launch sites across the world. Green ones are the active ones here in this diagram provided by the sounding rocket missions teams. I've mostly been working with what we've got. Let me put a wee laser pointer on here, hopefully you can see it. And what we've got in New Mexico here. But of course, the Wallops is where the home of sounding rockets, as was really originated from. But also I'm going to talk a wee bit about Alaska too, and the opportunities that are actually there. Of course, there's some here up, of course, in Norway and Sweden. A lot of those are to do with Aurora type experiments. And if you look at the various rockets they have, and this is really, you know, it's more than just toys for boys here, really. These really are sophisticated pieces of equipment, which you can use for lots and lots of different purposes. There's not just one rocket, there's a whole series as to where you want to get to, the height you want to get to, the elements of the size of the instrument that you're trying to carry. We mostly have been focusing upon this one here. This is the Black Plant 9. And I'm going to break down the various components here just to show you what a sounding rocket is like. But we'll base it on this one. In fact, if not all of what I'm going to talk about is based upon this specific rocket configuration. So here's the anatomy. Here's, you know, the bit where you take a rocket, you take it apart, and you try to understand what it's actually doing. So I'll work from the bottom up. Really, you have a first stage rocket here. That's what takes you off the launch pad. It's known as a terrier. It gives you an immediate kick, and that's what carries you off. You then have this bit here, particularly for the Black Brant. This is the second stage motor that fires to take you to the height that you want to go to. In our case, it's probably somewhere around about 130 to 150 kilometers, so something around about that. You then have this sort of section here. This is known as the transition section. It sort of mates the instrument bigger sort of area to what you've got with the booster rocket itself. It also helps to as a sort of absorb the impact when it lands again. And it has a way of separating the booster from the instrument. As you go up, you'll see that more in a moment. There's also, as you get into the instrument itself, which is in this bit here, there's a wee shutter door in here, which opens. It's a vacuum door, so you can open it in the vacuum of space, and you can use that for the telescope or your spectrometer to be able to point it towards the sun. The door is closed prior to re-entry, thank goodness, because you don't want to have that open when you're coming back down again. And then you have the experiment itself held within this sort of silver tube area, and that's provided by the researcher. You want to collect your data from there, and there's a whole range of instruments that can go into this particular part. This is where the main work from the science team is taking place. Still not finished, because just above that you have this little section here which is due to telemetry that helps to transmit your science data, but also important, your vehicle data down to the ground or the ground stations to understand what's going on. You then have booster guidance here. It's a system which helps to keep the vehicle programmed onto the track that you actually would want it. It works with the ACS, or the attitude control system, which is based here. For example, if you're doing a solar mission, you have a solar pointing attitude rocket control system with different sensors like magnetometers, gyroscopes, horizon sensors, that sort of idea to sort of know where you are. If you're doing a geospace one, then maybe you would have something like a magnetometer to align with the Earth's magnetic field, that sort of idea. Small jets of gas actually can come out of here to rotate your payload into the right direction. And I can give you your pitch and your yaw and your roll. That can all be controlled from there. And then above this, you have the recovery assembly, which is what helps you to be able to land and recover the instrument. It basically has a parachute here housed in the nose cone, and that's what deploys as it's coming back down to Earth. In the missions that we've been involved with, these rockets travel a distance of about 275 kilometers up and down, and right about a flight time of 15 minutes with a max speed of about 3 kilometers a second. So it really does fly, as you'll see. So as a wee cartoon, just to give you an idea, I'm sorry, this is the only one I can really find. It is a wee bit cartoony, but it gives you an idea. You do your first boost, you pass aircraft and high altitude balloons, that falls, and you do your second booster to take you up to the height that you want to be. But of course, that's less than a typical low Earth orbit because of where we are. And then you can point it towards the sun. So very basically, we have the various phases that you can have. This is just showing this in a slightly different way, because I'm going to actually show a movie in a moment where you're actually sitting on a rocket and you're going to be taken up, and you'll see the various stages as you go through. So phase one, as you can see there, is the launch itself down here in the bottom left. Phase two involves something called as de-spin and the payload separation. You are going to get some residue spinning taking place from the imparted from the launch vehicle, and essentially, you want to de-spin that, de-roll that really, and what you actually have is a sort of a mechanical yo-yo system, where there is cables which have weights on them, which are wrapped down in a certain way really, that unwrap as you go up, and that is a very effective way of de-spinning the rocket. Then you reach phase three, which is sort of getting up to here really, when you start to you open up the doors, you try to you're pointing things in the right direction to actually look directly at the sun. You're taking your observations at apogee, the main part of your flight path. Then the doors get closed, you were glad to hear, or maybe you've got some sort of boom or something if you're using sounding, other sounding work that gets ejected then, and you come back down to Earth, where the rocket payload lands. The payload reconditioned, and off you go again. Very much a sort of a reusable approach to getting into space. So let me give an example of this. You've got all the background now, you know the thing, what's actually going on. Let's see what we can do with these particular missions. Here's an actual rocket we've worked on. This is Magic's, to tell you about in a while, instrument. You can see it on the horizontal as they're working on it. There's the nose cone, there's the ACS, and you're getting down here to sort of telemetry systems. The box here is where the instrument is. It's in a shroud to keep it cool. This is in White Sands, and New Mexico. It's middle of the desert. You've got to keep it cool before you actually do the launch. Here's it from another perspective, where you can see the first rocket motor, the mating system there with the actual second booster leading into the instrument itself there, and there's the cooling tank to keep it cool. So that's what we see. So very similar to what I showed you in the little movie. We've changed a bit, but the ideas and the concepts of getting the fuel in and all that you have to do, and aspects of that is very much still there. Then you've got basically two rooms that you need to be in. There's one where you're looking at the launch and you're monitoring the sounding rocket itself, the actual launch process. This is known as the blockhouse. Here's the guys here sitting in front of their kit, looking to see how the launch process is actually going to be taking place. And you're in constant contact with them, with another room, which is mostly where myself and my colleagues would be, which is in the payload or instrument monitoring place. Here we have some photographs of us looking at doing what's going on. There's Amy down there, if you know Amy Weinberger and Liam Golub and others. This guy here is Ben from our team, not looking very happy there, really. I think he is, so he is. It is common and a sort of usually sign the rockets as part of the sort of process of what's going on, the tradition really of what's actually happening. This is actually the High C 2.1 flight. I'll tell you more about that in a moment. So there's the people, there's the rocket, there's the everything that you have in place if you're going to try and do something like this. Let me give you an example. So FOXY, you might have heard about, is the Focusing Optics X-ray Solar Imager. It's a suborbital rocket, of course. It's 3 launches so far. There's a 4th one coming, which I'll tell you about towards the end. It really is observing hard X-rays using focusing optics, and really has produced an imager that's probably most sensitive in the 4 to 15 keV range. And they are doing what we said previously, trying to pave the way for future spacecraft missions to use the technology. And it's very clear, actually, when you follow FOXY and the work by FOXY and Lindsay, who's the PI on this from the University of Minnesota, that there's significant developments in the optics and the hardware and the personnel between the launches. The image here on the bottom right is a image they got from this particular launch. But they put a camera on it on the launch of FOXY 3, and we're now going to follow this for about a minute and a half-ish, really. I'll try and talk over the various stages. Hopefully you'll be able to still hear me in that. It's only noisy at the start. There's also a bit of spin going on, so if you do get sort of sick with these sorts of things, you may want to sort of look away, but that'll slow down very quickly, and we'll actually get into orbit itself, and you'll see what happens. Okay, so let's go. Let's actually take a ride on FOXY 3. If it goes, and they're going to show us it from different angles. Let's see from another one. Okay. I think if you see the second boost on this one, I think it goes into the cloud before that actually occurs, unfortunately. Clear day, you can see the second booster actually going off. We're now sitting on the rocket itself, and off we go. Here's the spinning, taking place. That will set the down, and there we are. There's the release of the, and it starts to settle, and then it all goes quiet, as Bjork says. So now we're out in heading towards the apogee. The voice control system is having, I'm not too sure what that was actually, that wee ping going off. Maybe some of the Foxy team could tell me. You can see the Earth from the camera. It's pointing that down, and the other sort of the camera here pointing towards the target, the sun. Here's a wee movie showing the various targets that they did pick out relative to their pre-launch plan. And this is when you're sitting on the ground, you're seeing you're actually getting photons on your detector, which is excellent. It shows you actually it's working okay, and you're picking up a picture of what is actually being taking place there. But you've got to return to Earth again, and so here we go. Here's the 29. Spinning around, going through the atmosphere. Now it's slowing down a bit. You see the parachute on the left there has deployed. So we're more in a bit of a real-time situation here. We're getting closer to the ground. You can see the shadow there of the parachute and the sounding rocket. And bang, and you follow. And now you wait. And the instruments, as you fly out on a helicopter, sometimes they're repurposed Hueys, and you can collect your instrument, put it in the helicopter, and bring it back to the base. So there's the guys there, they're saying it. Hey, well done, the Foxy team. So it's around about 10% of our sounding rockets actually have a solar physics component to it. It's a lot more in the geospace arena, as you could probably imagine. But let me go through a couple of these with you, and to give you some of the science that we've been involved with by using the sounding rockets in ways we could never use with the other instrumentation we've got available to us. In particular, in this case, looking at coronal dynamics on a sub-arc second scale. So just give you an idea, yes, this is from White Sands. You can see it there, the missile range. Here's yours truly outside of it. This is the only holiday pic I'm going to show, you'll be glad to know. But it is really there. And as a foreign national, I have to be escorted everywhere, even to the toilet. But there you go. This is the high resolution coronal imager. An UV imager, you can see the various components. I'm not going to go over too much of a standard in some respects, but it has to do with the camera, which for HiC1, which I'm going to show here, was UCAM purchased and part of what's going on. But the light comes in through, hits your first mirror, secondary mirror, and then focuses down into your camera. So what do we get from that? Well, the bandpass for HiC1, this was 193 angstroms, very similar to SDO, but it had a much more sensitivity, greater effective area, as you can see here. And also, of course, it's the actual discovery space. The resolution, the pixel resolution, is about 5 times better than what we have with AIA, and with a cadence of about 5.5 seconds. It really is, something which can observe a space both temporally and spatially that's beyond what we would expect for AIA. But will we see anything different? Well, here's the launch team, a cast of thousands here. Maybe you could pick out yours truly and others. This was led by Jonathan Certain, actually. There's Liam Golub, there's Amy down the front, Kelly Corrick and others, and the UCLan team. And we launched, we landed, and we gathered the data, and this is the sort of thing you can actually see. So this is AIA, and AIA will zoom in on the particular parts of the region we see, with AIA on the left and HiC on the right, and you can see change, the superior spatial resolution that you actually have here with high C. But remembering the fact that actually when we got the data and we did check things out, you really only have about 2.5 minutes worth of usable data. But the difference is striking compared to what you see here and the threads that you see in the ideas of the complexity of the EUV corona. And I'm just sampling various bits here to show you, that there are things that we're picking out here in high C that you wouldn't see necessarily in AIA. But of course, because you see it in high C, you can actually go and look at AIA, and it actually helps you to pick out some of the things that you would want to focus upon. It really does lead you to and guide you to areas of interest. The high C1 data has resulted in about 26 journal papers, really. One instrument paper as well. I've put a link here, which if you can show the slides as I will later on, you can go to, and you can see the different areas where people have looked at. Let me just very briefly give you some ideas of that. One of the more, I suppose, famous ones, but some people say controversial ones, was the fact there was an argument that we'd actually seen braided reconnection. We'd actually seen the threads actually joining together, braiding with each other across what was a sheared Palladium version line. Here's the HMI magnetic field of the region we're seeing here, where with AIA in these lines, okay, and then high C here, and you can see the difference in resolution, that there was a sort of braiding effect. And then after the high C observations had finished, there was a significant release of energy. You can see it in this little movie here with the high C being in this one, which only runs for a short period of time. Hopefully it will repeat, but you start to get the braiding taking place, and then there's a release that you would see elsewhere. I suppose if you were looking at these images without having high C, you may not necessarily have picked this out, or picked out this specific point where maybe braiding is actually taking place. So is this a first direct second observation of a fine thread braiding in the corona? You can measure the speed that's taking place. You can look at the temperatures from ice, which we're also looking at this region at the same time. And there are other hints of other parts of the field of view that have some sort of loop-loop interaction. I would say that it's been challenged a wee bit by David Ponting, who with these numerical models indicated that the observed, what you see from an observed braided field may not necessarily be or look braided. They can't guarantee that, but at least give us something to idea and show the capabilities. You're doing something with a sounding rocket that you can't do with current space-based instrumentation. A few more just to show you the power of this. This is some work about bidirectional flows in filaments. That help these sort of threads and these flows, when we observe them, help us to understand the structure, help us to understand the mass exchange between the chromosphere and the corona, say, etc., etc. Here's the IC field of view where we see lots of little threads, but you can see what you see in 304 over here as well. It's wrapped around this lovely sunspot, really, that you can see. Here's an image, a VHF image from Big Bear. And so this was, and I hope this really, you can see that. So this movie didn't come out as well as I'd hoped, but here's the high C field of view, and we're arguing that this flows backwards and forwards there, which you actually can see in AIA and in a similar sort of wavelengths if you sort of screw up your eyes and really look for it, which again shows you that when you have this sort of resolution, you can see things, which leads you to also be able to analyze them in AIA. But I don't think you would necessarily trust AIA by itself in this sort of approach. You can cut across this and see the fact that AIA looks at one structure, high C has a couple of structures in there, and therefore that does make a difference when you are trying to understand and to model these sorts of features. We get anti-parallel flows around about 80 to 70 to 80 kilometers a second. The velocity shows there is spatial coherence taking place. That's so these are flowing along those structures are these commonplace within filaments. And of course, Iris and others have been giving us some wonderful observations of filaments as well recently. But it gives you an idea of the sort of thing that Hi-C can actually do. And finally, and just because I think it was a lesson more than anything else, is some of these sort of bright dots and sparkles that we saw. Here's the AIA movie of the sort of an open sort of fan region. There's little dots and stuff around that, and you think, well, is that just something to do with the data itself? Is it really there? Of course, you come into Hi-C and you do see it's actually there. There is these sort of small scale brightenings at the base of these very large, long loops. Let me just focus upon those brightenings itself. Here's the top left is Hi-C itself, and it's filtered out. They are definitely happening now. You can see hints of them in AIA, but would you analyze them the same way as you'd want to do here with Hi-C? Well, we have, and you can look at the profile of these over time and how they match in with some of them with other lines, ones you see in AIA. So this is time and sort of arbitrary intensity. You can look at the extrapolated magnetic field. Really, these sit in an area of predominant negative polarity, and therefore there must be the presence of some unresolved here from HMI fragments, which are hitting the base of these particular structures, and the base of these long feed lines in order to heat up or evaporate or whatever the material up into these sort of structures in order to give you the signal that you're getting. So because of that, we were very fortunate to be given a Group Achievement Award for Hi-C one. Not just me, everybody got one of these. A new capability, the sort of thing you want to do with a sounding rocket. So we tried to get the team back together again. We got the band back a couple of years later. Here we all are once again with Hi-C. We did everything we did before. We had a really good idea and it didn't work. It failed. And we received no data. The rocket launched, everything seemed to work well, but we just didn't get any data. And part of the reason for that, as we can see down here at the bottom, this is connected to the shutter, and there was a pinching of the wire just here, which shorted out the shutter, and it stayed closed. And this is what you get with sounding rockets. So sounding rockets, you can fail fast, I suppose. We probably should have checked this. You would maybe checked it in other ways, but you're all working with the team, you're learning, and also the fact that these things happen, and we've learned from that, and we check it again. As Niall Horan, that famous Irish philosopher and member of One Direction, said, everyone gets that second album syndrome. And I suppose it is. Your second album is always difficult, and rocket science is difficult. But it's a process of learning from it and from actually what we can do next within it. And of course, because it is a sounding rocket, 2 years later, we did. This is the high resolution coronal imager 2.1, which was launched in May 2018. Here we're looking at 172 angstroms emission, slightly larger pixels than we had before, slightly smaller field of view. And we captured around about 300 seconds worth of data. Let me show you some of the images from that. So here we got a very nice active region slap bang in the center of the sun, which was great. Let me see, let me just go back a bit actually. And lovely area where you could break down the various elements into different regions for what's actually going on. David Brooks had done some work in the previous IC data to look at loop widths and trying to get the widths across the various basic structures. And Marcus Schwaden and Hardy Peter had done a similar thing with Monte Carlo simulations and said, well, Hi-C should see around about a mostly strand width of about 550 kilometers. So we decided to test this. This is we work with Thomas Williams at ABBA. Tom's here today, where you can break the Hi-C field of view into different regions and try to get the widths out of that. And of course, what you see in SDO compared to what you see in Hi-C can be and is often very different. So let me just drop my laser pointer here for a minute. Here's some time average slices, which gives you an idea of what's going on across various bits and pieces of the loop. The red is AIA, with the black being Hi-C. And there is a real difference. There's a real difference in regard of that. You know, you get a broadening with AIA, but you actually get some real peaks seen with all the structures seen with Hi-C. It's resolving strands of material that you wouldn't see otherwise. In fact, you can take I suppose a histogram of the observations we have, and the top row being Hi-C, the bottom row here being AIA strand width against number of strands, and you can see that Hi-C 2.1 really is picking up strands and threads, which you wouldn't see with AIA. But the sort of peak is somewhere between 300 and 500 kilometers, which is the sort of thing that Marcus and others were sort of looking at. I'll jump ahead here to this one, hopefully, to give you an idea, that, is there for Hi-C resolving some sort of spatial scale in the corona? It probably is, but with 2.5 minutes worth of data, it's sometimes difficult to say that for definite. Hi-C is about 8 or 9 publications at the moment, an instrument paper. Again, when I share the slides, you'll be able to see what's going on. Okay, I'm just sorry, time is really racing, so I'm going to jump into, which one should I do? This one here. And this is another mission we're involved with, which is called the Marshall Grazing Incidence X-ray Spectrometer. So you don't just have to use images, you can also use a spectrometer. And really what we're trying to do here is determine the heating frequency of loops in active regions, whether the heat really has a high frequency or has a low frequency, because there appears to be a difference in what you would observe. Really, we're trying to fill a blind spot here in the spectroscopic coverage, and you're trying to look for the initiation of small-scale heating events and the response thereof, not just often what we have in cooler EUV lines, the material cooling down into that bandpass. With MAGICS, you get something called as an overlapogram, which I'm not going to go into here, but you're trying to disentangle the lines that you have versus the spatial resolution of what's actually going on. But there should be a difference if you have high frequency and if you have low frequency of heating taking place. So off MAGICS went just last year. And we were part of the team at UCLan, and the target that we had, this is the rectangular box here, is the field of view of MAGICS, and the 2 active regions in it were really good. The primary target there is, we thought, this is great, this is exactly what we would want. If I rotate that so it's more horizontal, then you get to see the within the instrument, we had a slit jar, which allowed us to see the pointing, so we knew where things would be and what we should actually see. That was the plan. Here's the execution. Unfortunately, due to some alignment issues within the telescope, there was a lot of stray light, and we couldn't see where we were pointing. We think that dot there is where you are on the sun here, so there's an optical flip, of course, also taking place. If you deconvolve the images, hopefully, let me see where we are. Let me see, deconvolve the images. That was just in a minute. Yep. Then you can see where things are, and actually we've shifted up to the north. So we're a bit unfortunate about that. Also, the optical axis wasn't exactly where we thought it was going to be. It's going to be shifted across. So if you look at the right-hand side here, that's only the effective area we got, which isn't great. In fact, we missed the target by a couple of arc seconds. But we still got spectra. so it was really good. It gives you an idea of the fact that this instrument is actually working, and you can compare that with high C, with AIA, and get an idea that you're in the right sort of field of view, particularly with the intensities you're looking at. But we weren't able to do the things we wanted to do due to the stray light and the pointing, and we weren't able to observe the brightest active region, and hence get the iron lines that was required. But Magix 1 was a very successful proof of concept. We developed technologies were developed that wouldn't have been developed otherwise. You can see here, and this is a slide Amy put together to show from previous developments through to where we are now, how that helped other missions to launch. And then, of course, we now have what we think is the beginnings of an X-ray spatial instrumentation that could go on a satellite. So I've given you a whistle-stop tour through sounding rockets there. I know we've only got about 10 minutes left, and so I'm going to use about 2 or 3 minutes of that just to tell you what's next, because we're always progressing what we've got, and there's always opportunities to get involved. And I've just talked about Magix and the problems that we've had. So Magix is going to fly again. It's going to be flying in about a year from now, probably in 2023. And the top sketch here was of Magix 1. The bottom here is a much reduced, probably slightly easier system that we had previously, which therefore helps to support the alignment better. And there's a pointer back. The spatial resolution is increased, the spectral resolution is also increased, and a sort of wider field of view and a higher throughput, because beforehand we had a slit in here, but it had to go to a slot in order to actually get enough photons through. So learning from what's happened previously, Magix 2 is launching in 2023, and hopefully with all the pointing work that our institution has been doing in particular, we now will not have the stray light to mean we're just simply firing blind, as it were. But also there's another exciting campaign known as the Solar Flare Sounding Rocket Campaign. And, not going to go over the physics of solar flares. You probably heard that in other talks, you know what's going on. But there is an argument that with the instrumentation we've got at the minute, we can maybe make some incremental improvements, but actually we maybe need more design breakthroughs to actually sort of take place. And therefore, if you're looking at designing new high energy instrumentation, you've got the additional requirement, of course, that you need to go above the absorption layer of the Earth's atmosphere. Now, sounding rockets can do that, but there are unfortunately significant issues with it. One of which is has severely limited the development of sounding rockets for solar flare research, has been the fact that if you have a rocket on the platform at the tower, you can only hold it for about an hour, particularly when you're at white sands. White sands, they close off roads around it, all this sort of stuff. It's a really big operation to launch that. You also have associated with that the short duration flight of a rocket. 5 minutes of observations. So the chances of you capturing a solar flare during that sort of time period is very, very limited. In fact, that's the reason why no instrument has really been designed for solar flare measurements via sounding rocket. And if you did capture one, the chances are that the instrument, the detector, would be swamped, would be saturated, because it's optimized for lower emission activity. So how do you sort of deal with this? Well, this is where Lindsay and Amy and Kathy Reeves have come up with this idea to actually have 3 sounding rockets, optimized instrumentation for observing solar flares, but launching it from Poker Flats in Alaska, where we can actually put these rockets on a holding platform for 4 hours a day for several weeks. This is all a bit mad, really. There's 3 instruments involved in this. There's the high C rocket, there's Foxy, and something called SNIFs. This is the Solar Eruption Integral Field Spectrograph, which has a range of individuals involved in it, and it's new actually, so I'm not going to go into that too much, but it shows you new technology developments are being made sort of available. IC3 is part of that. It's we're going slightly higher spatial resolution cadence by a second and a half, but now the passband is around 21 129 angstrom line at about 11 million degrees Kelvin. We have also something called Couliad, which is a spectrometer at the same sort of same line in temperature to try and work with that. And there's actually a student-led from Montana State University full X-ray detector, very similar to the GOES X-ray detector, but with much significantly higher cadence. So we're going to go to Poker Flats with this. And we have to do this in March 2024. So all the instrumentation has to be done, all the development, all getting it in March 2024. And that's because there's an excellent alignment with Parker Solar Probe and Solar Orbiter. And along with SDO and Hinode and ARAS and ground-based instrumentation, this is an incredibly complex and probably the most involved set of solar observations that have taken place. And the big question is when you press the big red button, when do you actually launch? And you know, that is a big issue for us. You need to predict in some respects when a solar flare could potentially occur. That's really, really difficult to do, of course. And we've got a program running alongside of that of different algorithms, different approaches, different work that's actually going on to do that. And you've also got the fact that you need probably about 10 minutes from pressing the button to actually launch, just because of safety features and everything around that. And then you've got another 5 minutes until probably you take your observation. So there's a lot of constraints there. But to actually be able to point this instrumentation while a flare is probably maybe just happened, if we can catch it as it's happening, just as about to happen, then that would be brilliant. But that's something very, very difficult. The solar flare sounding rocket campaign really is taking the sounding rocket capability to its limits. There's a sounding rocket symposium happening on the 17th to 19th of August. If you want to find out about that, you can go and see that, and maybe there's aspects of that you could be involved with and find out about yourself. But as I race towards the finish, and I'm sorry I've gone about 10 minutes longer than I wanted to, I'll just finish with Werner von Braun. Again, started with him, I'll finish with him. Sounding rockets give us an opportunity to do something very specific, very targeted, but really push science forward, make that step change. And we can have all the aspects and models and thoughts of what's going on, but as von Braun said, one good test is worth 1,000 expert opinions. And so I hope that I've given you an idea of what sounding rockets are like, how a good test can actually make a big difference. And maybe you'll join us and on sounding rockets, or watch out for what Magix and HiC3 are going to do next. That's all for this morning. Thank you for your patience, and thank you very much for listening. And actually, if you want to download, sorry, I should have said, if you want to download these slides, click on go to the QR code, and you'll be able to see these for yourself. Thank you very much. Sorry, Chris, I forgot about